Good morning, my dear friends. Now we shall go to the another problem in this shear. Okay, I will read the problem. This a cantilever girder 300 mm by 800 mm in cross section has a span of 8 meter. Okay, so it's a cantilever beam. It has got a span of 8 meter and carries a point load of 150 kilonewton at its free end. Okay, it is pre-stressed with 7 identical cables, out of which 3 are situated at 100 mm from the top, 2 at 200 mm from the top, and remaining 2 at 100 mm from the soffit. Each cable consists of 8 wires of 7 mm 5. Okay, and effective pre-stress in the cable is 700 Newton per mm square. Okay, determine the principal tension at 50 mm above centroidal axis at the support section. This is what he has asked now. Okay, so now we'll try to see what he has given in the problem. See now, I will explain you the problem. See now, it's like this. So it's a cantilever beam, as you know. Okay, at the free end, there is a point load of 1,50,000 Newton, and it is of 8 meter. This thing now, okay, span. See now. So now its cross section is 300 mm by 800 mm is the cross section. Okay, and since it is a rectangular section, I can easily mark the CGC. Am I right now? CGC can be now easily marked as 400 mm and 400 mm. Is it right or not now? And now what he says, there are 7 cables. These 7 cables are placed like this. 3 cables are placed at 100 mm from the top, and 2 cables are placed at 200 mm from the top, and 2 more cables are placed at 100 mm from the soffit of the beam. Soffit means bottom. Okay, so like this the cables are distributed in the this thing now. Understood or not now? Okay, cable distribution also is given in the problem. That is what I have marked here now. Okay, see now, now I think you can easily calculate the area, etc., etc., moment of inertia, etc., etc. So we'll try to see now. See now I think area can be now easily calculated. It is 300 mm by 800 mm. Okay, this I is BDQ by 12. That also can be calculated, and WD, in the sense it is the dead load. Okay, zero point 0.3 into zero point 0.8 is the cross sectional area into 1 meter along the span. It will give me the volume. Volume into density will give me WD. Okay, so this WD is the dead load, is now acting as a UDL. Am I right now? This acts as a UDL on the beam, 5760 Newton per meter. Okay, so now this only I have shown it in the problem as this thing now. What now? As UDL, which is now acting. Okay, see now. So the UDL acting is shown here now. 5760 is the UDL which is now acting. Along with this, there's a point load of 1,50,000 newtons. Okay, see now. So but now, what he has asked is, now he has asked you to find out the principal tension at the support section, because at the support section, since it is a fixed, since it is a cantilever beam, at the fixed end, maximum shear force exists. Am I right now? Maximum shear force exists at the fixed end. So at the fixed end only, I have to analyze the this thing. And what he has said is, now you have to you have to take a element at 50 mm above CGC. The element is now here. Okay, element is lying at 50 mm above CGC, and this cross section is at the fixed end here now. This is what he says. Okay, so now I want to now calculate the shear force at the support. Okay, at this point I want to calculate the shear force. So now it is just addition of all the loads, 1,50,000 plus 5760 into 8. Okay, sir. Now that will give me the total load. So shear force at this cross section is 196080 newtons. Okay, and now I want to calculate the bending moment at this fixed end also now. Okay, bending moment at support. Okay, so now since it's a cantilever beam, my this thing will be now minus Okay, so now 1,50,000 into 8, force into lever arm, okay, force into lever arm, minus this load 5760 into 8 is the total load, and it is acting at the center here. Lever arm is now 4 meter. Am I right now? So 5760 into 8 into 4, it will give me minus 1384320 Newton meter. This is your bending moment at the fixed end. Okay, so now, but also see now, Baba, as you know, CGC can be now easily located because it is a rectangular section, symmetrical one. CGC can be now easily marked as at 400 mm, I can easily mark. But as you know, but now since the cables are distributed unevenly at this cross section, CGS I have to locate. CGS has to be now located. Is it or not now? So what I assume is now each cable is having unit area. I will take the area of this cable as 1. This is 1. This is 1. Okay, so now this is also 1, this is also 1, this is also 1, this is also 1. In sense, its area is unity. I will take it as. Okay. So now, uh, uh, so if all I want to find out the CGS, I want to take the moment about the top. Moment about the top of all these cables. Okay. So y bar is equal to, okay, see now on the top here 1 2 3, in sense area of this cable plus this plus this, 3 is the area. 3 into lever arm up to the top is the 100 mm. Is it or not now? Lever arm up to the top is 100 mm. So into 100 plus 2, 1 and 2. 2 is the area. Its lever arm up to the top is 200 mm. Okay, plus 2 here, 2 here, lever arm up to the top, it becomes 700 mm, divided by summation of the areas. Here 3 areas plus 2 areas plus 2 area, 3 plus 2 plus 2. So it will give me 300 mm from the top. In the sense, your CGS lies at a distance of 300 mm from the top, y bar. Okay, here I have written 300 mm. Okay, so 300 mm is your CGS. Where is your CGS? CGC? CGC lies at a distance of 400 mm. So but now I think the distance between CGC and CGS is your eccentricity. So eccentricity can be now easily calculated. 400 minus 300 will give me the eccentricity as 100 mm. Am I right? So that also I have marked here now. You can see, okay, eccentricity is now 100 mm. Okay, so the same thing is now here now. Okay, also see now. Now the pre-stressing force I want to now calculate. By pre-stressing force is given by Fs into As. By Fs he says that it is 700 into As. But now he says wire is of 7 mm 5. Okay, so it is pi d square by 4. Such 8 wires are there in one cable. Am I right now? Into 8. Such how many cables are there? 7 cables. Am I right? 1, 2, 3, 4, 5, 6, 7. So 7 cables are there. So this will give me AS, area of steel. Okay. So your pre-stressing force is so much. Okay. Now let us consider, as per the problem, we shall consider the section at the fixed end, and my element is at 50 mm above CGC. Element is now here. Okay, so on this element I want to calculate the principal tension. Is it or not now? So now we'll try to calculate it now. See now. But now, since the cables are straight, okay, they are not going to contribute anything to the principal tensile stress. Am I right? Therefore, shear force in concrete is V is equal to Vc. In sense, whatever we have calculated earlier, shear force, same thing, it will remain. Okay, 1960. Okay, 1960 itself is your shear force in concrete. And by A y bar, I think I can easily calculate. A y bar is, it is the hatched area. Element is now here. This is the area above this 11. Okay, so 300 mm into how much now it is now? 250 mm. Is it or not now? So that will the area area into lever arm is from here to here. Okay. So a y bar can be now easily calculated. Okay. Breadth, as you know, it is 300 mm. I also you know. Okay, you have calculated. So now tau c can be now easily calculated. It is VC a y bar divided by IB. So all the values are known. So you can easily find out the value of tau c. But now sigma x can be written as f by a plus or minus fey by I plus or minus mty by I. Okay. So now I will go on filling the values now. Here now f I know, area I know, again f I know, eccentricity, as you know, it is now 100 mm plus 100 mm it is now, because it is below, it is above CGC. Okay. Y is 50 because y is above CGC. Your element is at 50 mm above. Okay, so it's plus 50. Plus 50. I know. Okay. MT, the bending moment you have already calculated, but your bending moment you have to give a negative sign because it's a cantilever. Okay. So Y I know. Okay. Again I. So it will become sigma x is equal to 1.46. Since vertical pre-stressing is absent, sigma y is absent. Sigma y is 0. So now I want to now calculate the principal tensile stress by this equation. Okay, you know this equation very well. So fill up all the values, sigma x you know, sigma y you know, tau c you know. Okay, and find out the value of this principal tensile stress. That is what he has asked. Okay, thank you very much.